Everything you can touch, this desk, the air you're breathing, even you, it's all held together by chemical bonds. They are, without a doubt, the most fundamental force in our everyday lives. But have you ever stopped to wonder what they really are?
I mean, it sounds like such a simple question, doesn't it? But the answer? Oh, the answer is so incredibly complex that for decades, chemists have relied on two really powerful and sometimes totally competing models to even begin to explain it.
So, let's meet our two contenders. We have valence bomb theory and molecular orbital theory. Now, the key thing to get right away is that it's not about one being right and the other wrong. A better way to think about them is like a wrench and a screwdriver. They're both super useful tools, but you really got to know which one to pick for the specific job you're trying to do.
All right, so let's pop open this toolbox. Before we can figure out when to use the wrench and when to grab the screwdriver, we need to understand how each one is actually designed. We're going to start with the core philosophy of each theory, basically how each one sees a chemical bond.
First up is valence bond theory, or VB theory for short. This is probably the one you remember from your first chemistry class, and for good reason. It's beautifully simple. It just says, look, a bond happens when two atoms get close, their individual electron orbitals overlap, and boom, they share a pair of electrons right in that little overlapping space. The magic word here is localized. The electrons belong to that specific bond and they pretty much stay put. To make this even clearer, just imagine two friends. Let's call them atom A and atom B. They decide to share one specific book, and that book is their electron pair. It only gets passed back and forth between them. It's a private, direct agreement. That, in a nutshell, is a valence bond. Okay, so now let's look at the other tool, molecular orbital theory, or MO theory. This one, it takes a totally different approach. It's much more of a big picture kind of theory. It says that when atoms come together to form a molecule, all of their atomic orbitals, they all merge and recombine to create a brand new set of orbitals that belong to the entire molecule. So the electrons aren't stuck between just two atoms, they are delocalized. They're free to roam. So if VB theory was our two friends sharing one private book, MO theory is like a huge public library. The books are electrons. They don't belong to any one person. Nope, they're part of the entire library system, and all the atoms can access them from anywhere in the building. It's a completely communal, system-wide approach. See the difference? So let's just boil it down. It really comes down to this one fundamental difference in perspective. Valence bond theory sees a molecule as a collection of individual, localized little bonds between pairs of atoms. But molecular orbital theory, it sees a molecule as a single, unified thing, with electrons just spread out all across this delocalized system. Okay, knowing the philosophies is a great start, but talk is cheap, right? The real test of any scientific model is whether it can predict what's going to happen. So let's put these two tools to the test and see how well they actually describe what we see in the real world. And this, my friends, is where things get really interesting. Because in some cases, one model works beautifully, while the other one just completely and spectacularly fails. So let's take a look at a really famous example. Let's think about the oxygen molecule, O2, the stuff we're breathing right now. If you draw it out using the simple intuitive rules of valence bond theory, you get a nice double bond where all the electrons are neatly paired up. Now, a key rule in chemistry is that if all your electrons are paired, the molecules shouldn't be magnetic. So VB theory makes a very clear, very confident prediction. Oxygen is not magnetic. But then we do the experiment. And it is so cool to see. When you pour liquid oxygen between the poles of a strong magnet, it sticks. It's paramagnetic. This is a huge problem. That simple, intuitive picture from VB theory is just, well, it's plain wrong in this case. It completely hits a wall. And this is where molecular orbital theory just swoops in and saves the day. When you build the MO diagram for O2, its more complex, system-wide approach predicts that oxygen actually has two electrons in separate orbitals that are unpaired. And what do unpaired electrons cause? Magnetism. MO theory's prediction? It matches reality perfectly. It absolutely nailed the oxygen puzzle. And this oxygen thing isn't just a one-off fluke. This pattern holds true for all sorts of other complex properties. For a molecule like benzene, for example, VB theory has to invent this special patch called resonance to make it work. MO theory, it handles it naturally with its delocalized orbitals, no problem. For bond strength, MO theory gives us a precise calculation called bond order. And, as we just saw with magnetism, MO theory is the undisputed champion. So,
After all that, you might be thinking, okay, Mo theory is clearly the winner, right? Let's just toss VB theory in the trash. Well, not so fast. This brings us to our final verdict. It's not about finding a single winner. It's about understanding which tool is right for which job.
And here's the practical guide, the cheat sheet, if you will. Do you just need a quick, simple, and intuitive picture of a molecule's 3D shape and its basic connections? Then use valence bond theory. It is fantastic for that. But are you trying to explain more complex stuff like magnetism or why things have color or systems with widespread electron sharing? Then you need the more powerful, more comprehensive tool, molecular orbital theory. And that right there is the most important idea to take away from all of this. These are models. They're our best human-made descriptions of an incredibly complex reality. Neither one is the absolute truth. A good scientist doesn't have one favorite tool. They have a whole toolbox, and they know exactly which one to pull out to solve the problem that's right in front of them. Which, of course, leaves us with one final, kind of mind-bending question to chew on. If both of these incredibly successful theories are really just useful approximations, what does a chemical bond actually look like, deep down, beyond any of our models? Well, that's the kind of question that keeps chemists pushing the boundaries of science every single day. Thanks for exploring it with us.